All right, we're going to explore number systems. So our number system that we used is called the decimal system. Decimal having a prefix deci, that means that this is a base 10 system. Not only is it base 10, it is what we call a place value system. So each of those two things meaning something different. The base 10 part means that there are 10 digits that we use to write all of our numbers. Those digits are 0, 1, all the way up till 9. Okay. Every number we write is only made using those symbols. Okay. And I'm talking about them as symbols, not as actual numbers here. The place value part means that when I put these digits in a number, they take on different meaning depending on what place they occupy. So consider several examples, all containing the digit 2. Because the 2's are in different places, they mean different things. So in our first example, the 2 means 200. Okay. In our second example, it means 2,000. Here it just means 2. Okay. And here it means 2 hundredths. Okay. So different meaning for different place values. Okay. We're going to be primarily interested in whole numbers here, although it does extend to non-whole numbers. But for whole numbers, how far left of the decimal point you go actually corresponds to a power of 10. So instead of thinking of them as we did here, I would think of this as 2 times 100, or more properly, 2 times 10 squared, or 2 times 1,000, or 2 times 10 cubed, right? So everything is based off of a power of 10. Okay. So for instance, the number 237, if I write it in what is called expanded decimal notation, this is 2 hundredths, or 10 squareds, plus 3 tens, or 10 to the ones, plus 7 ones, or 10 to the zeros. Okay. Notice, everything is multiplied by a power of 10. The exponents are decreasing. Furthermore, notice that we have a 10 to the 0 as our last one, which is of course equal to 1. Okay. But we need to not forget that. Now, our system is base 10. Why? Well, it's a quirk of biology. We happen to have 10 fingers and 10 toes, so we were naturally drawn to the number 10. It does not make it any better or worse than a lot of other systems. Other cultures throughout history have used other bases. For instance, there are cultures that use base 5, 12, 20, or even 60. If you think 60 is a stretch, I will remind you there are 60 minutes in an hour and 60 seconds in a minute, which are a holdover from that very civilization. Okay. All right. So we understand our own system fairly well, but I wanted to explain this to compare it to the next two systems. In computer systems, base 2, otherwise called binary, is used very often. So base 2 will consist of 2 digits, so 0 and 1, okay? And again, we like these because a 1 can represent a closed switch and a 0 can represent an open switch. And so we can code things in binary just by switches. All right, so let's practice some with binary. Okay. The same number in decimal versus binary will be very different. And when we are speaking of different number systems and we want to make sure we know which one we mean, we will put a little subscript of the base. So this subscript 10 means that number is in decimal. The subscript 2 means that number is in binary. So on the left, this means 1 times 10 cubed plus 0 times 10 squared plus 1 times 10 to the 1 plus 1 times 10 to the 0, which is of course the number we typically call 1011. On the right, it will be 1 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0. Notice when you compare these, the only difference is that I wrote a different number as the base of the exponents, but the actual exponents themselves stayed the same. Okay, this is the similarities between the system. Okay. All right, so if I wanted to know what this number equaled in binary, I would plug this expression as is into a calculator, okay, or do it in my head. This is 8 plus 0 plus 2 plus 1, otherwise known as the decimal number 11. Okay. All right, so we will practice this conversion from binary back to decimal. Okay. Now you may ask, how did I know to start at 10 cubed or 2 cubed? Well, that's because that's how many digits there were. So we start counting from the right, incidentally, not the left, okay? And we always start counting at 0, okay? So I have a 0, 1, 2, 3, 4. I should start with an exponent 4. Most people forget to start counting at 0, even though I need it because I always start with an exponent of 0. They say I have 5 digits in this. If you choose to count all 5, just remember to start with one lower of an exponent. So 1 times 2 to the 4th plus 0 times 2 cubed plus 1 times 2 squared plus 1 times 2 to the 1 plus 0 times 2 to the 0. The point is the one on the right needs to start high enough so that my very last one always has a 2 to the 0 attached. Okay. So this is 16 plus 0 plus 4 plus 2 plus 0, otherwise known as 22 in decimal. One more just to make sure we have it. Okay. I count the number of binary digits. There are 6 of them, so I will start with a 2 to the 5th. This is 32 plus 16 plus 0 plus 0 plus 0 plus 1, otherwise known as the number we call 49. All right, it is significantly harder to go from decimal to binary. Binary to decimal was fairly simple. Going the other way is going to take more work. I might suggest you pause and go get a very good calculator. Okay. All right. So I'm going to start my first example with a very, very small number, 7 in base 10. So starting is the hardest part. What I need is the largest power of 2 less than or equal to 7, which means you need to be somewhat familiar with your powers of 2. All right, well, 2 is less than 7, 4 is less than 7, 8 is not less than 7, so the answer to this question was 4, otherwise known as 2 squared. All right, so we are now going to do 7 divided by 4. Okay, well, 7 divided by 4 gives me a quotient of 1 and a remainder of 3. And I'm doing quotient and remainder division, not decimal division. So the quotient becomes the number that I multiply by the 4, or 2 squared. The remainder becomes the number that gets carried on. So next I'm going to do 3 divided by 2. So again, the remainder 3 got carried on. The 2 came from, once I started with 4, I then do all powers of 2 less than that. Okay. So 3 divided by 2 is a quotient of 1 with a remainder of 1. Okay, so that will be a 1 times 2 to the 1. And the 1 will get carried on and divided by the next power of 2, which is 2 to the 0 or 1. So this will give me a 1 times 2 to the 0. Okay. Finally then, we ignore all the 2's and just write the numbers in front of them. That is 1, 1, 1 in binary. Okay. All right, now you may say, how am I going to do this on a calculator? When I do division, it gives me lovely decimals. I will explain how I do it. Okay, I would put 7 divided by 4 into the calculator. It'd give me 1 point something. So I wrote down the 1. Then I would do 7 minus 1 times 4, where 1 is that quotient, and that's how I'd get the remainder. Okay. All right, let us do another one. 53 base 10. So again, I'm going to start with the largest power of 2 smaller than 53. So I go up the powers of 2. 2, 4, 8, 16, 32, still good. 64, no longer good. So backtrack, and I'm going with 32, folks. 32, otherwise known as 2 to the 5th, is where I will start. All right, so in my calculator, I do 53 divided by 32, get a quotient of 1. So then I take 53 minus that 32, and I get a remainder of 21. So 1 times 2 to the 5th. Again, that's the quotient I'm lifting off. The remainder gets pushed to the next step. 21 divided by, and now I do the next smallest power of 2, which is 16. Quotient of 1, remainder of 5. So that gives me a 1 times 2 to the 4th. Quotient became the 1, remainder gets pushed to the next step. 5 divided by 8. Now you may be saying 5 doesn't divide by 8. I know, but you cannot skip the 8. 16, next power of 2 is 8. So 5 divided by 8 is a quotient of 0 and a remainder of 5. That gives me a 0 times 2 cubed. Okay. And the 5 gets stuck to the next step. 5 divided by 4 gives me a quotient of 1 and a remainder of 1. Okay. That gives me 1 times 2 squared. 1 gets pushed to the next step. 1 divided by 2 gives me a quotient of 0 and a remainder of 1. So that gives me 0 times 2 to the 1. The 1 gets pushed to the next step. Okay, but I'm at the last step, so that 1 simply becomes the final digit. Thus, in binary, this is 110, 101, base 2, where I'm lifting off the numbers in front of the powers of 2. Okay. All right, you got it? Let's do one more just to make sure. 458. Okay. So, the numbers are starting to get big enough that you may not know the powers of 2 by yourself. Okay, so pull out your calculator and start saying. Okay, 2, 4, 8, 16, 32, 64, nope, not yet. 128, not yet. 256, not yet. Our next number is 512 though, and that was too big. So I'm retreating to 256, which happens to be 2 to the 8th. Okay. All right, so my first division is 458 divided by 256, quotient of 1, remainder of 202. So that gives me my first binary digit. The remainder gets pushed on. 202 divided by 128 is a quotient of 1 and a remainder of 74. So that gives me a binary digit. Remainder gets pushed on. Okay. 74 divided by 64, quotient of 1, remainder of 10. Okay. 10 gets pushed on. 10 divided by 32, I can't skip things, quotient of 0, remainder of 10. 10 gets pushed on. 10 divided by 16, quotient of 0, remainder of 10. I've run out of room, so I'll go to the next line. Okay. So now 10 divided by 8 gives me a quotient of 1 and a remainder of 2. Okay. So I get my next binary digit. Okay. Then 2 divided by 4 gives me a quotient of 0, remainder of 2. Okay. Then 2 divided by 2 gives me a quotient of 1, a remainder of 0. This actually gives you your last two digits. The quotient and the remainder both become digits. So in total, reading them off, I have 1, 1, 1, 0, 0, 1, 0, 1, 0. Whew. I did warn you that direction was harder. Now, you can actually do arithmetic, that is adding, subtracting, multiplying, and dividing in base 2. Now, most times when I try to explain this to people, they're like, oh, it's okay, I'll just translate it to base 10, do it in base 10, and translate it back. But did you not just see how annoying it is to translate from decimal to binary? It is easier to just stay in binary the whole time. Okay. So, let's practice. Okay. Now, in what we're going to do, it's going to be helpful to have what I call a key. So, 1 in decimal is 1 in binary. Convenient. 2 in decimal is 1 0 in binary. Makes that very famous shirt. Okay. 3 in decimal is 1 1 in binary. How do I know these? Well, 2 is 1 2 and 0 1s. 3 is 1 2 and 1 1. Okay. These are going to come up over and over again. It's helpful to just not have to think about them. So I did them ahead of time and we'll stick them over here. All right, so let's start adding. The algorithm for adding is the same. That is the procedure. I'm just doing it with different numbers. So 1 plus 0 is 1. 0 plus 1 is 1, and 1 plus nothing is 1. As far as I can tell, that is no different between decimal and binary. Okay. It does, of course, get more interesting when I'm going to have to start carrying. Now, I will give you a hint. When you are working in binary, you are only ever allowed to write 0s and 1s, other than the tiny base 2. Okay. If you find yourself wanting to write something other than a 0 or 1, refer to the key and translate it. So 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 2, but I'm not allowed to write 2. So I translate it to 10, which is 0, carry the 1. 1 plus 1 is again 2, which I translate to 10. You see how this can get very confusing. Okay. One more addition problem. Zero plus 0 is 0. 1 plus 1 is 2, but I will write it as 10. I now have 1 plus 1 plus 1, which is 3. But my key tells me to write that as 11. 1 plus 0 plus 1 is 2. 1 plus 1 plus 0 is 2. 1 plus 1 plus 1 is 3. 1 plus 1 is 2. Okay. So I'm speaking the normal way. I am just translating them before I write them down. I could also do subtraction. Okay. Same algorithm. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus nothing is 1. I had to do nothing different because I didn't have to borrow. Okay. So if you do have to borrow, what do we do? 1 minus 0 is 1. I cannot do 0 minus 1, so I go to this 1 and make it a 0, and make this a 10. Only, see the key, 10 is really 2. So really, this is 2 minus 1, or 1. Okay. I can't do 0 minus 1, but it's easier to just say that I'm doing 10 minus 1 and take both remaining digits at once. 10 minus 1 is 1, because 10 is really 2. Okay. What did I do wrong? Nothing. I wrote wrong in my answer key. Okay. Yep, that looks right. All right, you know what's coming next. I'm going to multiply. Okay. Have no fear, I will stop before we get to division. 1 times 0. 1 times 1. 1 times 1. Okay. Put a placeholder of 0. 1 times 0. 1 times 1, 1 times 1. Add the results. Of course, making sure that you are entirely inside base 2. Okay. I don't know about you, I actually like this better. I'm really good at 0 times 1s and 1s times 1s. It's like 7s times 8s that are hard for me. Okay. All right. Let's do one more example of multiplication. I'm multiplying everything by 1, which is essentially just copy it down. Placeholder of 0, then multiply everything by 0. I like that. It's all zeros. I now need 2 placeholders. Multiply everything by 1, which is just copy it down. Then I add the results. 2, 2. I think I messed up. Let's backtrack. Yep. You'll actually find that if you do a lot of these problems in a row, you tend to start thinking in binary because it's easier. Okay, so I was literally going 1 plus 1 is 10 in my head instead of saying 2 and translating it. Okay. All right, so this is a very brief introduction to binary. You, of course, have recognized the problem with binary. It takes a really long time to write any number. Okay, these numbers are ginormous in number of digits, even though in size they actually would not be that big. Okay, so computer scientists said, well, we can kind of do a shortcut. Okay. So they use something called hexadecimal, otherwise known as base 16. Now, that's fine, except for I need 16 digits. And some crazy person, instead of saying, well, I will make up 5 new digits, which would have been the thing that I would have appreciated, they said, let's use letters. I don't like this because then I get confused if they're letters or numbers. But our 16 digits in hexadecimal are, well, the standard 10 first, 0 through 9. Oh, I totally forgot the 5. I knew I was going to forget something. Okay. The standard 10 first, and then I need 5 more. So they said, hey, let's use some letters. And I guess I need 6 more. I really can't count today. All right, for future reference, by the way, A means 10, B means 11, and so on. Yes, that is ridiculously confusing. All right, I'm not going to make you do quite as much in hexadecimal. We're just going to practice a little bit of conversion. So, to get a hexadecimal number back to base 10. So I know it is hexadecimal because of that little subscript of 16. Okay, I count how many digits there are. There are 4, which means my first digit must be multiplied by a 16 cubed, and then a 16 squared, and E, wait a second, we don't like that, so I translate and say never mind. I'm going to write a 14 for E times 16 to the 1. Again, B translates to 11 times 16 to the 0. Okay. We are not quite as good at doing these calculations in our head, because goodness knows I don't know what 16 cubed is off the top of my head. No, I plugged this straight into a calculator, and it told me it was 14,827 in our standard decimal number system. Okay. All right, one more practice. 1C, 0A, B, D, 7, base 16. So I start by counting how many digits I have. There are 7 of them. That tells me that my first power of 16 will be 6. So 1 times 16 to the 6. C, which is 12, times 16 to the 5. 0 times 16 to the 4. A, which is 10, times 16 cubed. B, which is 11, times 16 squared. D, which is 13, times 16 to the 1. and 7 times 16 to the 0. My calculator told me this was 29,404,119 in decimal. Okay. All right, don't worry, I am not going to make you go from decimal to hexadecimal. Instead, we are going to explore how it is actually quite easy to go between binary and hexadecimal. Okay. So, let's start with a hexadecimal number. Okay. Now, each of these digits correspond to a four-digit sequence in binary. Okay. It is somewhat convenient to just write out all 16 symbols in hexadecimal and write them down in binary. Okay. By the way, such a chart is on page 104 in the discrete math textbook, so you don't have to do it yourself. So I look up on that table and they tell me that 4 in hexadecimal, if I go to binary, is 0, 1, 0, 0. A is 1, 0, 1, 0, and so on. Then I string those all together. I can ignore the first 0, of course. To get my binary version of the same number. You notice, of course, why hexadecimal is quicker. Okay. It requires only 1/4 the number of symbols. Okay. We can also go the other way, by the way. So if I have a binary number, okay, I'm going to break it up into groupings of 4, okay, and then look them up on the table. Okay, it would help if I wrote down the same number that I have on my cheat sheet here. Okay, so 1001 became 9, 1101 became D, and so on. Okay, so in hexadecimal, this is 9DE7. Okay. All right. So as long as you have a translation table listing all 16 hexadecimal digits and their corresponding binary code, it is very easy to translate back and forth between the two systems.